Good afternoon, class. So last time we have deal with the agonist, that is alpha agonist and beta agonist. We have seen their SAR, the properties, their pharmacological activity of this agonist. Now we are moving to the next part, that is the antagonist, that is the adrenergic antagonist. Okay, so agonists are the drugs they can bind to the receptor and they can show the similar kind of effect what the neurotransmitter does. But the antagonist means the drugs or the antagonists are the chemicals which bind to receptor and they block the activity. They block the receptor so that the neurotransmitter can't bind to this receptor and will show the activity. So antagonists function only to block the receptor so that neurotransmitter cannot bind to the receptor. That way they block the action. Okay, so as alpha receptor they are classified into alpha 1 alpha 2, so the alpha blockers they are also classified into alpha 1 blocker and alpha 2 blocker. Similarly beta blockers they are also classified into beta 1 beta 2 and beta 3 blockers. So the uses of alpha blocker there is generally for the hypertension along with the diuretics they are used as the antihypertensive effect or they produces as the antihypertensive. So they are along with the diuretics they are given to reduce the high blood pressure to the bring it to the control. Then vasoconstriction, BPH, cardiac heart failure, phenochromatocytoma, renal disease. So such disease or such symptoms they can be utilized. They are using alone or they are using along with the combination of other drugs like diuretics in the treatment of hypertension. Now, we will generally found that in case of alpha adrenergic receptor antagonists, they are not like beta antagonists. That is, beta antagonist or the beta receptor blockers. What they do, they have the structural similarities with the neurotransmitter like adrenaline, noradrenaline, or isoproterenol. But in case of alpha antagonist or alpha adrenergic blockers, they consist of number of compounds with diverse chemical structures and they are having a very little or very less resemblance with the alpha agonist. Okay, so beta antagonist they are having the similar kind of structures because as we know that when the drug bind to the receptor they should have the similar kind of structure so that they can bind into the receptor or they have to block the receptor. So there some structure resemblance must be present in the receptor in the agonist as well as in the antagonist so they can bind to the receptor. So in case of beta receptor they having the structural similarities with neurotransmitters but the alpha receptor they have very little or less structural similarities with the neurotransmitter. Okay, so generally these alpha blockers they are classified into two types. One is the selective alpha blockers, they are generally selective alpha 1 blockers. Second one, non-selective alpha blockers, in that again irreversible alpha blocker and non-irreversible alpha blockers. Irreversible alpha blocker and reversible alpha blockers. So such alpha blockers can be classified. Okay, reversible means it consists of tolazoline and phentolamine. In irreversible, there is consist of a phenoxybenzamine, which is the prototype of the drug, along with the dibenamine. Okay, for our syllabus, phenoxybenzamine is there. This drug is not there for our syllabus. But for alpha blocker, selective alpha blocker, there are prozosine, teirazosine is also there, as well as doxazosine. Okay, so for our syllabus, there are two drugs as a alpha 1 blocker or the selective alpha 1 blocker. One is the doxazosine and another one is the prozosine. Okay, so prozosine and teirazosine they having the similar kind of structures, only the furan ring is reduced. That is the only difference between the prozosine and the teirazosine. Okay, so in case of irreversible blocker, they generally consist of beta halo alkyl amine type of structure. For example, phenoxybenzamine. So on the beta there is a halogen Cl is present, so it is beta halo. Two alkyl ethyl group is present, so it is alkyl, and amine is present. So beta halo alkyl amine groups is present in case of this one. Here you can find out that we have studied in the SAR of alpha agonists. There we have seen that the imidazole ring, if it is present in the structure, it can be given as an alpha agonist activity. So repeating upon that, these reversible blockers, they consist of imidazole ring, but the changes made there that in that structure they having the halogen atoms on the aromatic ring. Here there is absence of halogen atoms on the aromatic ring, as well as they have increases the length. There only presence of either carbon or nitrogen. Here presence of carbon along with the nitrogen, and this nitrogen binds to the two different groups or the aromatic groups, and these aromatic groups they having the substitution at the para position. So this lengthening the aromatic group, it makes them the antagonist. So in case of alpha 1 and agonist, alpha 2 agonist, they having the imidazole ring, but they having either CH2 or the nitrogen as a linkage. Here there is absence of halogen atoms. Along with that, after linkage, there is a bulky group or the bulky aromatic group which is present, which makes them a alpha blocker. Okay, so they blocks alpha 1 as well as the alpha 2. So please consider three things. One, selective blocker means they either block alpha 1 or alpha 2. Non-selective means they act on both alpha 1 as well as the alpha 2. And if you are saying mix, that means they act on alpha plus beta. So that is the difference between selective, non-selective and the mixed agonist antagonist. Okay, so mix means alpha as well as the beta. Selective means either alpha 1 or alpha 2. In case of beta, either beta 1, beta 2 or beta 3. So on all these three beta, then there is the non-selective beta blockers. All two alpha, then non-selective alpha blockers. Any specific alpha 1 or alpha 2 or beta 1 or beta 2 or beta 3, that means they are selective blockers. The non-selective alpha 1 blockers, they are non-selective and they can bind to the alpha 1 as well as the alpha 2 receptor. They consist of imidazole ring. That's why they are generally the competitive blockers. The structure of this you can find out. Tolazolin is similar to the imidazolin 1 agonist, but they don't have a lipophilic structure which is required for the agonist activity. Hence, this imidazole, instead of agonist, they become the antagonist. So the lipophilic part, if it is present in the structure, then this lipophilic part, it leads to the agonist activity. But here there is absence of lipophilic part in this imidazole ring. So instead of becoming alpha agonist, they becomes the alpha antagonist. In case of irreversible, that means when they block a receptor, then that receptor is permanently blocked. The reaction is not reversed. In case of reversible, suppose this is receptor. So reversible, they can bind to the receptor. After some times, they can be get removed from the receptor. But in case of irreversible, like phenoxybenzamide, when they bind to the receptor, the reaction cannot be reversed. So that is a permanently blocking of this receptor. So the such permanently blocking of the receptor, such drugs, they are called as irreversible alpha blockers. And as we have told, it consists of beta haloalkylamine in the molecule, which alkylate the alpha receptor. So they bind in case of anti-cancer, we are seeing nitrogen mustard. What they do? They are causes the alkylation of the nucleic acid. So here similar kind of mechanism takes place for the irreversible alpha blocker. They consist of a similar kind of structure, beta haloalkylamine, which undergo azidinium ions, and this azidinium ions is responsible for the alkylation of receptor. And when the alkylation of receptor takes place, the drug cannot bind to the receptor or neurotransmitter cannot bind to the receptor, and it will not show the activity. So similar kind of effect is shown by the nitrogen mustard as an anti-cancer, but they are responsible for the alkylation of DNA. Here the drug is responsible, or these alpha blockers, they are responsible to block the alkylates the receptor. So that is permanently blockage of this receptor takes place. That is the alkylating means it causes the covalent bonding, and covalent bond is strong bond. It's difficult to reverse this covalent bond. Hence, it is the permanently blockage of the receptor takes place. Example, dibenamine and phenoxybenzamine. Then we are moving to the next part, that is the selective alpha 1 blocker. So as the name indicates, selective. So this selective alpha 1 blocker, they act on alpha 1 receptor and they become alpha 1 selective drugs like prozosine, terazosin, doxazosin. So these are the drugs which comes under the selective alpha 1 blockers. These selective alpha 1 blocker, they block the alpha 1 receptor. Hence, they reduces the effect of alpha 1 adrenergic receptor. Okay, so as we have seen the structure, they consist of three groups in their structure. First one, quinazoline ring. Second one, piperazine ring. Third one, acyl moiety. So out of this amine group which is present at the fourth position, this amine group is responsible for the alpha 1 receptor affinity. Okay, so the drugs they consist of second part, that is the piperazine ring, but this piperazine ring or this moiety it can be replaced by piperidine without changing in the activity. That means there is no loss of activity if we are changing the piperazine ring with the piperidine ring. So there must be presence of this type of heterocyclic ring which is responsible to maintain alpha 1 receptor antagonist effect. Then this acyl moiety is responsible for the pharmacokinetic properties. So they are responsible to maintain the pharmacokinetic properties. So in that prozosine, terazosin and doxazosin, these are the examples. In the prozosine, what happens if this R group, all the structure is same, only this R group is replaced by furan. Okay, it becomes prozosine. Drug is prozosine. If this R group is replaced tetrahydrofuran, the drug becomes terazosin. Okay, and in case of doxazosin, there is the presence of benzene ring along with this moiety, and this part is R, then the drug becomes doxazosin. So these are the three examples which comes under the selective alpha receptor antagonist. Okay, prozosine if it consists of a furan ring, terazosin if it consists of tetrahydrofuran ring, and if this ring is present, it is called as doxazosin. So only the difference between these three drugs, this is as the pharmacokinetic properties. Okay, their bioavailability is different, their pharmacokinetics is different. Okay, so the prozosine is 50 to 70% bioavailability they having, but the terazosin, which is the reduced form, it having bioavailability nearly 90%. As well as if the reduced drug takes place, its half-life increases to 9 to 12 hours. So this terazosin having the half-life 9 to 12 hours as compared to half-life of prozosine, that is the 2 to 3 hours. And this doxazosin, it having the highest half-life among these three, it having the half-life of 22 hours and actually 36 hours of activity. So these changes in the structure, they are responsible to increase their pharmacokinetic property with respect to their bioavailability, half-life, and their duration of action. So doxazosin having the highest duration of activity as compared to the terazosin, as compared to the prozosine. So if you are going with the duration of activity, okay, so duration of activity, doxorubicin having more than terazosin than prazosin. And similar for half life. So doxorubicin having more half life as compared to terazosin and very less for the prazosin. So this is about the alpha 1 receptor blockers. They have the quinazoline ring at the fourth position, amine ring, which is amine group, which is responsible for the binding to the receptor. Then piperazine ring, it can be replaced with the piperidine ring, and this acyl moiety is responsible to maintain the pharmacokinetics property. So if R is furan, it is prazosin. If it is tetrahydrofuran, it is the terazosin. So they are responsible to maintain the pharmacokinetic properties. Now we'll move to the next part, that is the beta blockers. So the first beta blocker which was reported, it was dichloroisoproterenol. It having the similar structure like isoproterenol. If we observe the structure of isoproterenol, which is the beta agonist drug, so here hydroxy group is present, here hydroxy group is present. So such halogens, if they are replaced with the hydroxy group, it becomes isoproterenol, which is agonist drug. If we are replace it with the halogens, such drugs they are called as dichloroisoproterenol, which is the beta blocker. So this simple modification by changing the hydroxy group with the halogen, we can give a drug which having the beta antagonist. But it was found that this dichloroisoproterenol, it is beta antagonist, but along with that it shows some kind of agonist effect. So it is not a pure antagonist. So it is called as partial agonist. So along with the antagonist effect, it shows some kind of the agonist effect. Okay. So for the treatment, it is difficult to give such drugs because it may produces the antagonist effect along with the agonist effect. So we cannot find out which effect it can be produced. That's why it is necessary to go for the selective beta 1 blocker. So beta 1 blocker, they are present in the heart. We are giving for the antihypertensive effect. But if it is non-selective, means it is partial agonist, it can decreases or it can increases. So its activity is uncertain. So it is necessary to go for the development of clinically useful drug which is selective. So next drug important in the beta antagonist generation, it was pronethalone. It having a less symphatomimetic activity than these dichloroisoproterenol, but it is found that during the clinical study, it was found that it can produces thymic tumors in the mice. So after observing this type of side effects, this beta antagonist proresolol is not come to the market, or you can say it is withdrawal from the clinical trials, that it produces cancer, that is the thymic tumors. Okay, then the scientists Black and Stephenson, they have produces a new drug that is a beta blocking activity, and that drug is propranolol, and it is studied completely and it is widely used in the treatment. So that is the structure of propranolol. You can observe that here there is a hydroxy group is present, here is hydroxy group is present. So methoxy group is introduced in the structure, and this methoxy group which is introduced in the structure, it is responsible to produce its high level of beta blocking activity. So this propranolol belongs to the group of class that is called as aryl oxypropranolol amine. So you can observe aryl oxy, then 1, 2, 3, along with the hydroxy group, so propranolol, and finally amine. So such class of drug is called as aryl as aromatic group, then oxy as oxygen, propranolol as 3 propyl along with the methane, and finally amine. So it is a prototype of drug and it is the called as aryl oxypropanol amine. So here you can observe that methoxy group is incorporated in the structure which produces antagonist effect. So scientists they thought that so introduction of methoxy group in the chain it produces the beta antagonist effect, but it was not true. They found that it is not true. OCH2 group is present in most of the beta agonist drug also. So it cannot say that this OCH2 group is only the responsible for the antagonist effect. Later they found that the aromatic ring and its substitution is responsible for the determination or the responsible for the producing beta antagonist effect. So this aryl group is also responsible for the pharmacokinetic property along with the metabolism as well as the producing the beta blocking or beta antagonist activity. As well as the nature of this aromatic ring is determine its beta 1 selectivity. So the nature of aromatic ring is also responsible for the determination of beta activity. So aromatic group is responsible for the pharmacokinetic property. Along with that, it is also responsible for the beta 1 selectivity or to become a beta 1 selective. So one of the future of such beta 1 selective, they found that if para substitution is made on aromatic ring with sufficient size along with the absence of meta substitution, and if naphthol ring can be replaced with a single benzene ring, it can produces the antagonist or beta 1 antagonist effect. So the drug practolol is introduced. Practolol is introduced. So it having the structure like this one. Only the single benzene ring is present. In case of propranolol, there is a naphthalene ring is present. In pronetholol, it is naphthalene ring is present. But in the practolol, a single benzene ring is present, like the dichloroisoproterenol. And here there is the presence of NH, COCH3. Here methoxy group is present, and here the further hydroxy group, and here the further their substitution takes place. So they found that if there is no meta substitution and para substitution is there with proper size, the drug can becomes a beta 1 selective antagonist. That's why for the cardiac selectivity we require beta 1 antagonist. So they found that such type of substitution, if we are making in the drug, it can become a beta 1 cardio selective drug. But in the fact that it produces some toxic effects. So the proctalol produces some toxic effects. Hence, such drug is withdrawn from the clinical trials and it is not present as a cardioselective beta 1 drugs. So in this way, the development of different drugs takes place, and they found that in the blockers, if bulky aliphatic groups such as tertiary butyl and isopropyl groups are present on the amino group, here you can see propyl group is there. In some structure, butyl group is there. So if such bulky group is present on amine group, it becomes beta 1 receptor antagonist, and the drug and the group must be the secondary amine. It should not be the tertiary or primary amine. It must be the secondary amine. That means NH group must be present as it is, and to the nitrogen 1 carbon along with that there are 3 carbons. So the propyl group or the tertiary butyl group is present, which can show the beta blocking activity. Okay. So in case of SAR, most of the beta blockers They are allyloxypropranololamine, as we have seen in this. The two carbons are chains are essential for the activity, and secondary amines is responsible for the optimum activity. So here must be presence of NH group to make it secondary amine. Then aryl group is present, this oxy group is present, and the carbons they are present. It is responsible to shows the optimum activity. So at least two carbon must be present in the side chain to show the optimum activity. It can be three, but it should not be less than two or more than three. Then the configuration of hydroxy group. If hydroxy group is present, what happens? This carbon becomes chiral, and they having one hydroxy group, hydrogen atom. At one side there is aromatic ring, at other side there is a amine group is present. So it becomes hydroxy group. It becomes the carbon group attached to the hydroxy. It becomes a symmetric center. So it gives two types of isomers with S configuration and R configuration. So these enantiomers with S configuration, they found that it is 100 times more potent as compared to the R isomer. So R propanol is less active. Sorry, R propanol is less active with respect to S propanol. This S propanol is 100 times more active as compared with the R propanol. So it is less potent, it is more potent. If more lipophilic groups are present, then it can enter into the CNS. So as we have studied, if the lipophilic group is present, it can cross blood-brain barrier, and when it crosses blood-brain barrier, it enters into the CNS and produces the side effects. Hence, if more lipophilic groups are present, it enters into the CNS and causes CNS side effects. So propranolol, labetalol, these are the drugs with higher lipophilicity. Intermediate, these carvedilol, acebutolol, and atenolol, nordanolol, sotalol, these are the drugs with low lipophilicity. Okay, when to the groups, if larger bulky groups are present, okay, if such groups are present, then the drug becomes mixed blocker, that is it can block the alpha 1 as well as the alpha 2 blocker. Okay, so if carvedilol, labetalol, you can find out such type of bulky groups at the end which is responsible to produces the alpha 1 blocker, alpha blocker as well as the beta blocker. Okay, so this is the SAR of beta antagonist in short. First part, amine group, it must be the secondary with branch. It may be the secondary, should not be primary or tertiary. If bulky groups are present, along with that, it becomes mixed antagonist. That is alpha as well as the beta. Then this hydroxy group is present, and this carbon becomes chiral center or asymmetric center. So R and S, two isomers are present. Then this aromatic ring determines the beta receptor blocking potency. It is also responsible for the selectivity. So only the para substitution are present and meta substitution is absent. In such kind of drug, it produces the beta 1 selective. So if drug is lipophilic in nature, it can cross blood-brain barrier and it can show side effects which are related with the beta blockers. Okay, so this is about today's lecture. Okay, so alpha blocker, their SAR, beta blocker, their SAR, we have seen. In the next lecture we will see what are the drugs comes under the alpha blocker as well as the beta blockers.